All right, let's get right into it. Picture this. We've been handed a vial containing a sample of a totally pure but completely unknown element. So our mission, should we choose to accept it, is to become atomic detectives. We're going to figure out exactly what this element is by uncovering its most fundamental secrets.
Now, before we start our investigation, we've got to know what we're actually looking for. You see, our picture of the atom has changed a lot. Way back when, scientists imagined this plum pudding model you see on the left, basically just a blob of positive stuff with electrons dotted around inside. But then, Rutherford's model on the right totally changed the game. It gave us that dense, positive nucleus right in the center, and that discovery pretty much laid the foundation for the modern atom we know today.
So, here's our game plan. First, we're going to nail down what a modern atom actually looks like and figure out the secret address of its electrons. Then, we'll hit our first complication, these atomic imposters called isotopes. To sort them out, we'll use a high-tech racetrack, analyze the results, and then use one final, crucial clue, what I like to call the electron's escape energy, to definitively crack this case.
Okay, so Rutherford's model was a huge breakthrough, but our modern understanding is, a bit more detailed. We now know about neutrons hanging out in the nucleus, and this is absolutely crucial for our case, that electrons don't just zoom around randomly. Nope, they live in very specific energy levels, kind of like the layers of an onion. And understanding these layers is the very first key to unlocking our element's true identity.
What's so cool about this is that an electron's location is anything but random. Each and every one has a specific address inside that atom. And get this, that address determines the element's entire personality. We're talking its chemical properties, how it reacts, the whole shebang. So if we can just figure out this address, we're going to be a huge step closer to identifying our suspect.
Think of it like this. These electron shells are the main streets in an atomic city. Street number 1 is right downtown, closest to the nucleus, and it's the lowest energy real estate. As you move out to streets 2, 3, and so on, you get further from the center and the energy level goes up. Each street also has a strict occupancy limit. It can only hold so many electrons.
All right, let's zoom in a little closer. On each of these main streets, or shells, you've got different types of houses. We call these subshells. The ones we'll run into most are labeled S, P, and D. The S-type house is the simplest, with the lowest energy. Then comes the P-type, and then the D-type. It's kind of like a hierarchy of housing on every single street.
And if we go one level deeper, inside each house are the rooms, which we call orbitals. These are the actual zones where you're most likely to find an electron at any given moment. And there is a very strict rule here. Each room, or orbital, can hold a maximum of 2 electrons, no more. An S house, just 1 room. A P house has 3 separate rooms, and a D house has 5.
So how do the electrons decide which rooms to move into? Well, there are 3 basic rules of the road. First, electrons are kind of lazy. They always fill up the lowest energy spots first. Second, like we said, max of 2 electrons per room, and for them to share, they have to have opposite spins. Just think of one pointing up and the other pointing down. And third, if a house has multiple empty rooms, each room gets 1 electron before any room gets a second one. No one likes a crowd if they can help it.
So, just when we think we're getting a handle on this, our investigation hits a snag. We take a closer look at our unknown sample and, well, we find that not all of its atoms have the same mass. What's going on? It looks like we're dealing with a case of atomic imposters.
These imposters have a name. They're called isotopes. And here is the single most important clue of the day. An element's identity is defined only by its number of protons. That's its atomic fingerprint. It's non-negotiable. So, all the atoms of our mystery element will have the exact same number of protons, but they can have a different number of neutrons, which just means some of them are a little heavier than others.
Just take a look at these 2 forms of titanium, for example. See that? They both have 22 protons. That's what makes them titanium, period. But notice the number of neutrons is different, 24 versus 27, which changes their mass. And yeah, the one on the bottom is also an ion. It's lost a couple of electrons, but its fundamental identity is still titanium because it's got those 22 protons.
So, how in the world do we separate these different weight isotopes to figure out what's really in our sample? We use this incredible piece of tech called a time-of-flight mass spectrometer. The easiest way to think about it is as an atomic racetrack. We're going to make all our atomic suspects run a race, and we'll identify them based on how long it takes them to reach the finish line.
Okay, this race has 4 main stages. First, we have to turn our atoms into positive ions so we can actually control them with electric fields.
Then, we line them up and accelerate them, giving every single one the exact same amount of kinetic energy. After that, they fly down a long straight tube, and finally, they smack into a detector at the end, which times their individual races and counts how many of each type of atom finish.
Let's look at that first step, ionization. To even get our atoms on the track, we need to slap a positive charge on them. For a simple element, like the one we're investigating, we use a method called electron impact. It's basically like atomic billiards. We shoot a high-energy electron at our atom, which knocks one of its own electrons off, leaving behind a positive ion. That other method, electrospray, it's just a gentler technique they use for really big molecules that might otherwise shatter.
All right, now for the acceleration stage. And this is the secret to the entire race. Every single ion, I don't care how heavy or light it is, gets blasted by an electric field and is given the exact same amount of kinetic energy. So since kinetic energy equals 1/2 mass times velocity squared, if they all have the same energy, it means the lighter ions have to end up moving faster than the heavier ones. It's just physics.
The race is over, the dust has settled, and our detector has all the data. Now comes the fun part, analyzing the results. This printout, which we call a mass spectrum, holds the key to cracking the code and finally putting a name to our unknown element.
And here are the official results from our race. The MZ column is pretty much the mass of each isotope that was in the race, and relative intensity, that just tells us how many of each finished. So, our sample has 4 distinct isotopes, with masses of 82, 83, 84, and 86. And you can see right away, the isotope with a mass of 84 is the clear winner. It's by far the most common one in the bunch.
Now for the final calculation that's going to unmask our element. We need to find the weighted average of all these masses, which is called the relative atomic mass. So we multiply each mass by its abundance, add all those numbers together, and then divide by the total abundance. We punch in the numbers and we get a definitive value, 84.1. So we pull out our list of suspects, the periodic table, and there it is. Our mystery element is krypton.
Case closed? Well, not quite. Any good detective will tell you to always confirm your findings. We've got one last piece of evidence to look at, the energy it takes to pull electrons away from the atom one by one. This is called ionization energy, and believe it or not, it connects all the way back to that electron address we were talking about at the very beginning.
Take a look at this graph. It shows the energy price to remove the first electron, then the second, then the third, and so on. Notice how it's a pretty steady climb at first, right? But then, look, between removing that 4th and 5th electron, there's a massive jump in the energy needed. That huge leap, that's our smoking gun.
So what's that jump telling us? It means those first 4 electrons were all snatched from the outermost shell. They're the furthest out, the easiest ones to grab. But to get that 5th electron, we had to break into a brand new inner shell, one that's way closer to the powerful pull of the nucleus. That's why it takes a crazy amount of extra energy. This pattern confirms that our suspect krypton has exactly 4 electrons in its outer shell, its valence electrons.
And there you have it. The case is officially solved. The electron address gave us the rules of the game. The isotope imposters forced us to run our atomic race, which gave us the element's average mass, pinpointing krypton. And finally, that electron escape energy confirmed its electron structure, locking it into place. Every single clue pointed to the exact same suspect.
It's pretty amazing when you think about it, right? How just a few fundamental principles can let us uncover the identity of something as tiny as a single atom. It really just leaves us with one final big question. If we can understand the absolute building blocks of matter with this much precision, what are the limits to our ability to shape and engineer the entire world around us?